A bat swoops through absolute darkness at 40 miles per hour. It dodges stalactites using echolocation. Its survival strategy has worked for 50 million years. Then, in 1/10 of a second, it's gone, snatched mid-flight by legs that materialized from nowhere. The hunter weighs less than a nickel but just captured prey 10 times its size. This is the giant cave huntsman spider. With a 12-inch leg span and reaction times that rival professional athletes, it's mastered a hunting technique that shouldn't be possible for an arthropod, capturing bats in mid-flight from ceiling perches. No light, no binocular vision, just ultra-sensitive hairs detecting air movement and hydraulic legs deploying in 18 milliseconds. These ceiling assassins are hunting in one of Earth's most challenging environments and winning. If you want to see how physics-defying this gets, smash the like button and let's dive in. From the get-go, let's look at what these spiders are working with. The giant cave huntsman, primarily from the genus Heteropoda, measures 8 to 12 inches across with legs extended. That's the diameter of a dinner plate. The body alone spans 2 inches, and specimens weigh between 4 and 7 grams. To put that in perspective, they're hauling around the weight of a nickel while controlling a skeletal system larger than your hand. Each leg contains 7 segments connected by hydraulic joints powered by hemolymph pressure. This allows instantaneous extension at speeds reaching 8 feet per second. Research at the National University of Singapore found that huntsman spiders can deploy their legs from folded to fully extended in just 18 milliseconds. That's 3 times faster than a human can blink. The legs terminate in specialized tarsal claws with microscopic serrations, over 2,000 per claw, that grip irregular cave surfaces with enough force to support 20 times their body weight. Cave huntsmen lack the large eyes of jumping spiders. Instead, they've invested in mechanoreception. Their legs are covered with Trichobothria, ultra-sensitive hair-like structures that detect air displacement from distances up to 16 inches. These hairs can sense vibrations as subtle as 1/10 of a millimeter. When a bat flies past, it creates pressure waves and wing-beat frequencies around 12 to 15 hertz. The spider's Trichobothria lock onto these signatures like radar. The venom contains neurotoxins that target the mammalian nervous system, specifically affecting sodium channel function. Unlike tarantula venom designed for insects, huntsman venom evolved to subdue vertebrate prey. Studies at James Cook University identified compounds that cause rapid paralysis in small mammals within 30 to 90 seconds. The venom also contains digestive enzymes that begin breaking down tissue immediately, though these spiders typically consume their prey whole rather than liquefying it externally. Cave huntsmen use a hunting strategy called ambush sprint. They remain motionless for hours, then explode into action when prey enters their strike zone. Their maximum sprint speed across vertical surfaces reaches 15 inches per second. That's functionally instantaneous across the 3-foot strike radius most individuals maintain. They accomplish this on smooth, moisture-covered limestone that would defeat most climbers. Recent behavioral studies suggest these spiders demonstrate spatial learning. Researchers at the University of Queensland documented cave huntsmen returning to successful hunting positions after disturbances and adjusting their positioning based on prey traffic patterns over multiple nights. One individual adjusted its location by 42 inches over 3 weeks to optimize its position beneath a bat flyway. This suggests memory formation and environmental mapping far beyond simple stimulus-response behavior. The prosoma, the front body section, contains hydraulic systems that generate the pressure needed for explosive leg movement. The opisthosoma stores metabolic reserves, allowing the spider to survive weeks between successful hunts. Their exoskeleton is reinforced with chitinous cross-bracing that distributes impact forces when catching prey traveling at high speed. But here's what makes this truly extreme. These spiders hunt upside down while clinging to cave ceilings, which means every capture involves absorbing momentum that's trying to rip them from their anchor point. Now let's examine why bats, masters of aerial agility, become victims. Bats present a unique challenge because they evolved specifically to avoid predation. Their flight capability, echolocation, and nocturnal lifestyle made them largely untouchable to terrestrial predators for 50 million years. Yet cave huntsmen exploit critical vulnerabilities that only appear in cave environments. Echolocation limitations. Bats navigate using ultrasonic calls that bounce off objects and return as echoes. However, this system has a fatal blind spot. Echolocation works by detecting surfaces and calculating distance from echo delay. A motionless spider pressed flat against a textured cave ceiling returns an echo virtually identical to the rock surface behind it. Research at the Leibniz Institute for Zoo and Wildlife Research found that stationary objects smaller than 4 inches diameter are functionally invisible to echolocating bats at ranges under 6 feet. The spider becomes visible only when it moves, which happens after the bat is already within strike range. Flight pattern predictability. Inside caves, bats follow consistent flight paths determined by tunnel geometry. A study in Gomantong Caves, Malaysia, tracked over 2,000 bat transits and found that 78% of individuals use the same 3-meter-wide corridor when exiting the roosting chamber. This creates predictable hunting lanes. Spiders position themselves along these flyways, essentially setting up ambush points on an aerial highway. Bats can't deviate significantly without risking collision with cave walls, limiting their evasive options. Speed-agility trade-off. The bat species most vulnerable, primarily Hippociteros and Rhinolophus genera, fly at speeds between 25 and 45 miles per hour inside caves. At these velocities, their turning radius exceeds 6 feet. If a spider attacks from directly above at a range under 4 feet, the bat literally cannot maneuver away in time. Its own speed becomes a liability. Slower flight would allow tighter turns but would cost energy efficiency for the 2-mile journey most species make between roosts and feeding grounds. Visual dependence in transition zones. Near cave entrances where dim light penetrates, bats reduce echolocation call rates and rely more on vision. A 2019 study in Thailand's Khao Yai Caves documented that bats decreased echolocation pulses by 62% in twilight zones. This is precisely where many Huntsman spiders position themselves. The bats are essentially flying through a sensory dead zone, too bright for optimal echolocation, too dark for effective vision. Size vulnerability. The bats most frequently caught weigh between 8 and 15 grams, roughly twice the spider's weight. Larger species like Eonycteris spilia at 40 grams are rarely taken, while smaller species around 5 grams are too energy inefficient as prey. This creates a vulnerability window where bat size is large enough to be worthwhile, but small enough to be physically manageable for the spider. Metabolic constraints. Bats operate on razor-thin energy budgets. They can't afford to significantly reduce flight speed or add extensive detours to their routes, even if it would improve safety. A paper in Journal of Experimental Biology calculated that reducing cruising speed by just 15% increases cave transit energy costs by 34%. Bats are evolutionarily locked into flight patterns that spiders have learned to exploit. So how do these two interact? The answer is a predation sequence that lasts less than 2 seconds but requires perfect timing. The hunt unfolds in approximately 1.8 seconds from detection to feeding. Phase 1, 0 to 0.6 seconds. Detection and positioning. The spider detects the bat from 12 to 16 inches away through Trichobothria sensing air displacement. Wing beat frequency and approach angle give the spider roughly 0.6 of a second to prepare. During this phase, the huntsman shifts its body weight slightly toward the direction of approach and adjusts leg angles to optimize strike trajectory. High-speed video captured by researchers at Chulalongkorn University shows the spider's prosoma tilting up to 8 degrees, preloading the hydraulic system for explosive extension. From this range, the bat remains unaware. Its echolocation returns show only ceiling texture. Phase 2, 0.6 to 0.9 seconds. Strike initiation. When the bat enters the 3-foot strike zone, the spider launches. The first and second leg pairs extend simultaneously at 8 feet per second, while the third and fourth pairs maintain ceiling grip. This creates a 7 to 9 inch interception net positioned directly in the bat's flight path. The spider's timing precision is extraordinary. One study measured strike initiation timing variance at just plus or minus 12 milliseconds across 47 successful hunts. The spider essentially calculates a 3-dimensional intercept point and deploys its legs to occupy that space point, 3 seconds before the bat arrives. Phase 3, 0.9 to 1.2 seconds. Capture and restraint. Contact occurs at the bat's shoulder or wing membrane. The tarsal claws lock into flesh and membrane instantly. The bat's momentum, approximately 200 times the spider's mass moving at 35 miles per hour, creates impact forces exceeding 40 times the spider's body weight. The spider's exoskeleton absorbs this through chitinous cross-bracing that flexes up to 11% without fracturing. Simultaneously, the extended legs pull the bat toward the spider's fangs while the rear legs maintain the ceiling anchor. The entire spider bat system swings in an arc, but the attachment point holds. Phase 4, 1.2 to 1.8 seconds. Envenomation. The chelicerae, fangs, penetrate the bat's body, typically at the neck or thorax. Venom injection delivers approximately 0.3 milligrams of neurotoxic compounds. The bat's wing beats become erratic within 3 seconds and cease within 15 seconds. Paralysis progresses as sodium channels in nerve tissue malfunction. Within 90 seconds, the bat is immobile. The largest documented capture occurred in Deer Cave, Borneo, in 2017. A huntsman with an 11.2-inch leg span captured a Hippociteros diadema weighing 14 grams, 3.2 times the spider's weight. That's equivalent to a 150-pound human catching a 480-pound object mid-flight. The spider maintained its grip and consumed the bat over 18 hours. But the implications of this predation go even deeper than individual hunts. This predation reveals critical dynamics in cave ecosystem energy flow. In caves with high huntsman densities, up to 12 individuals per 100 square meters of ceiling, bat mortality rates during nightly exits reach between 2 and 4%. A colony of 5,000 bats could lose up to 200 individuals monthly. This represents significant population pressure. In Naya Caves, Sarawak, long-term monitoring shows bat population levels inversely correlate with spider abundance, suggesting these arachnids function as meaningful bat predators despite their size disadvantage. Each captured bat represents a transfer of nutrients from outside ecosystems into the cave. Bats feed on insects and fruit externally, then bring that energy into caves as roosting sites. When spiders predate bats, they're intercepting nutrient flow and redistributing it within the cave through their waste products and eventual death. This supports cave-adapted invertebrate communities that feed on spider frass and remains. Cave huntsman populations appear stable across their range, though habitat degradation affects specific populations. Guano harvesting operations that disturb bat colonies indirectly impact spiders by reducing prey availability. Scientists at the Max Planck Institute are studying the neural processing that allows these spiders to calculate three-dimensional intercept trajectories without binocular vision. Early findings suggest distributed processing across the leg nervous system. Essentially, each leg contributes to spatial calculation. This could inform robotic motion planning algorithms. We still don't know the maximum size bat these spiders can successfully capture or whether individual spiders specialize in particular bat species based on flight characteristics. Future studies may reveal learning mechanisms that allow spiders to refine hunting techniques across their lifespan. What makes this particularly fascinating is that it demonstrates predation can evolve in reverse. Prey that escape to the air can be pulled back down by predators that never truly left the ground. Giant cave huntsmen represent extreme predation through biomechanical precision and sensory adaptation that compensate for massive size disadvantages. These spiders catch prey 10 times their weight traveling at highway speeds using nothing but hair-like sensors and hydraulic legs that deploy in less time than a human blink. The most remarkable measurement: they maintain success rates around 30 to 40%, despite hunting in complete darkness against prey that evolved specifically to escape predators through flight. We still don't fully understand how their distributed nervous system performs the calculations needed for mid-air interception without centralized visual processing. But if you think ceiling ambushes are extreme, wait until you see spiders that hunt underwater using diving bells made of silk. That biomechanics makes this look simple. Click the video on screen. If you want more extreme predation content, hit subscribe and turn on notifications. We explore the most fascinating hunting strategies on the planet. Thanks for watching. See you in the next one.